Hello, everyone. My name is Marco Pavone. I'm one of the organizers of the Robotics Today seminar series. And I'm excited that Robotics Today is back for the fall with an exciting set of speakers. And in particular, it is my great pleasure to announce the first speaker for the fall, namely Matt Robinson from JPL. Matt is a senior member of the Robotic System Group at the NASA Jet Propulsion Lab, where he has been since 2001. He has a lot of expertise with Mars missions, in particular in the context of surface missions. And most recently, he has been the deputy manager in charge of the design, development, and delivery of the sampling and caching system for the Mars 2020 rover.
I want to make sure we convey how excited we are about the mission, and hopefully you'll be excited by this mission as well. I don't consider this just a NASA mission. This is a mission owned by all the United States and also the rest of the world in the science community and engineering community. So we all should feel part of this mission. So I thought I would start out with a brief montage of the building of the Mars 2020 rover to give you a little bit of an insight into what it took to bring about a mission of this magnitude. So the images that you're seeing are images from the high bay at the Jet Propulsion Lab in Southern California, in Pasadena. We're seeing the assembly of the cruise vehicle. And this is the 25-foot chamber where we do environmental testing. One of the things that I would like to say is that many people made this mission happen, both in the United States and internationally. At JPL alone, there are thousands of engineers that participated in making this happen. We have partners around the world, both scientists and engineers. So it's really exciting, and that's why I say this is a mission not just for the United States, but for the entire world. We all should feel ownership of this project. Okay, just a brief introduction about the Mars 2020 mission. The Mars 2020 rover was named Perseverance as a result of a nationwide contest of students from kindergarten through 12th grade. And the winner who was selected was a 7th grader named Alex Mather from Virginia. And part of the contest involved writing an essay. And I wanted to quote a small snippet from his essay because I think it makes it has special meaning, I think, given the state of things in the United States currently. Alex says, "We as humans explored as creatures who could learn to adapt to any situation, no matter how harsh. We are a species of explorers, and we will meet many setbacks on the way to Mars. However, we can persevere. We, not as a nation, but as humans, will not give up. The human race will always persevere into the future." Now, the winner of that contest, Alex, was announced in early March before the whole COVID pandemic really broke out in the country. Just looking back at the Perseverance name, we realize how apt that name was. Not only did the team persevere as we went from concept to design and then fabrication, test, and then finally launch, there were a number of challenges that we had to overcome to get to that point. But then, lo and behold, 6 months before launch, we had this curveball thrown at us from out in left field that no one could have even anticipated with the COVID. And I think that just shows that the Perseverance name how apt and how amazing and how fitting that name is. Um, okay, so we're going to walk through a little bit of the background of the Mars 2020 mission, and I'll give you some background of why we're going to Mars and what we were hoping to learn there. And then I'm going to dive into some more details about the sampling and caching system in particular. From a robotics technology standpoint, um, the robotics in the Mars 2020 mission may not be considered state of the art in terms of the latest and greatest. However, in terms of practice, the state of what I would call the state of practice for robotic sampling in extreme environments, it's right there at the forefront with the challenges. We send a rover from here to another planet. Once it goes, there's no coming back. So you have to be ready to face whatever curveballs Mars will throw at you. As we'll discuss, Mars is a very tough environment. It's a tough place to explore, and we have to be ready for that. There's no calling AAA if we run into problems. We have to have whatever tools we're going to have to face those challenges have to be there. They have to be in place. Okay, this is an artist's depiction of the timeline for Mars 2020 missions since 2001. And as the timeline indicates, we've been exploring Mars pretty much continuously now for about 20 years. We've had a continuous robotic presence on the surface of Mars for about 20 years, going back to orbiters such as Mars Odyssey, and then rovers on Mars, such as the Mars exploration rovers, Spirit and Opportunity. One thing I'll point out here is on the ExoMars rover, this picture depicts it as 2020. That mission did get delayed until 2022, but we're looking forward to it getting to Mars as well, as an engineering and a space exploring country in a space exploring world. So why do we explore Mars? Well, for one reason, Mars is our nearest neighbor. As we branch out and explore the solar system and beyond, it's really just natural to start with Mars. And in many ways, Mars is like Earth. Mars has an atmosphere, it has seasons. If you look at Mars in terms of the land area, Mars actually has the same amount of land area, of dry land area as the Earth, despite being about half the diameter of the Earth. So as we branch out and search for life in the universe, it's just natural to start with our nearest neighbor. Now, Mars exploration at NASA for these missions has followed a theme called follow the water. And why follow the water? Well, we know that water, based on our experience on Earth, water is necessary for life. It's fundamental for life. Life requires water. Also, water is an important agent for geological change. It's a force that drives geological change. And water is a key component to both climate and to climate processes. Stepping in and then looking at our evolution of rovers on Mars, what you see in front of us are 3 generations of Mars rovers. Starting with the 1996 Pathfinder Sojourner rover. To give you a sense of scale, the Pathfinder Sojourner rover is about the size of a microwave. It had a single instrument on the end of it and a very simple robotic mechanism for deploying that instrument. Jump a few years later, and then we had the 2003 MER rovers Spirit and Opportunity. The rover increased both in size from Sojourner and also in terms of capability. It carried with it a robotic arm, which was called the Instrument Deployment Device, about a meter long, 5 degree of freedom arm. And at the end of it, it had a number of tools and instruments for performing scientific investigations. Then a number of years later, we had the 2011 MSL Curiosity, which was then another leap forward in our progress of Mars exploration. MSL was both larger in size. We went from a MER-sized rover, which was about the size of, I'd say, a golf cart or a large lawnmower type, riding lawnmower, so to speak, to now the Curiosity rover is about the size of a small SUV. From a robotic perspective, the robotic arm now is about the size, is about twice as long as what the MER IDD, it's the length of the MER IDD. It also carried a payload that was more than 15 times more massive. And the Curiosity mission, not only did it perform contact science, but it had onboard science laboratory capabilities where it could process samples and determine the constituent elements of minerals and the composition through onboard chemistry. So there's plenty of evidence that water flowed on Mars in the past. About 3.5 to about 3.8 billion years ago, Mars and Earth were much more similar. Evidence that we've collected from those Mars missions has helped support the idea that Mars was once it contained much more water. There was liquid water present in the distant past, around 3.5 to 3.6 billion years ago. In fact, Perseverance's older cousin, the Curiosity rover that we just saw, explored the habitability of Mars. What it found there were nutrients and energy sources that microbial life could have used as a food source and building blocks to support life. It also established that Mars had regions that could have been friendly to life in the distant past. So from Follow the Water, our missions are progressing towards search for signs of life. Again, previous missions have indicated that Mars once had what life needs. Now we're going to look for signs that life existed. If we look back on Earth, to around the same time frame, 3.5 billion years or so ago, that's when scientists found, they found evidence that life, microbial life, began to form on Earth around that period, around 3.5 billion years ago. So the questions are going from the Earth, using Earth as an analog for what Mars, because we knew that Mars was likely very similar to Earth back then. Did life ever exist on Mars? And if microbes were present on Mars in the planet's ancient past, are there areas on Mars where it could exist today? And even if microbial life never existed, a major goal of this mission is to look for habitats that could support potential future human exploration of Mars. So the Mars mission has the Mars 2020 mission has a number of objectives. There are really four main objectives. One is carry out measurements to characterize the geology of the landing site. We're going to study rocks and soil at various scales from the macroscopic down to the microscopic level. We want to understand how and why they formed and use that to determine the history and the origins of where the rover is going to land. The second goal is to determine the habitability of the ancient environment. We want to assess whether the environment was capable of supporting microbial life in the past. We want to seek signs of possible past microbial life. Those signs are what we refer to as biosignatures. And we want to search for rocks that would preserve those signs of life over time. We also, furthermore, our third main goal, which is what I'll focus on today, is to collect samples. We want to collect samples by coring into rocks and collecting soil samples. And then we want to prepare them for future return to Earth. Looking for signs of life and determining that life really did exist is a very intricate process. And many times it requires scientific instruments that would fill up an entire room. It's very difficult to shrink that down to the size of an instrument that could fit on a Mars rover. So we're aiming to do the next best thing, which is to bring the samples back for processing here. And then finally, we want to prepare for human exploration. We want to measure the temperature, humidity, wind, and the dust environment to understand what the effects might be on human health and on our ability to have humans have a presence on Mars. And there's also an instrument called MOXIE, which is to demonstrate in situ resource utilization. And that instrument is designed to convert CO2 and O2. And of course, O2 is something we need to breathe and also can be used as fuel to return back to Earth. So where are we going? The Mars 2020 rover is going to Jezero Crater. Jezero Crater was selected by a team of scientists. They had a number of workshops, and then ultimately they zeroed in on Jezero. Jezero was believed to be the home of a lake, that the crater was actually filled up with water. And what you can see there's an inlet as water flowed into Jezero, and also an exit where water could flow out. And based on observations of what elements are there in Jezero Crater, they believe that this crater actually was filled with water, and that water was stable at some point in Mars's past. As we send our rover there to explore, we can look at rocks that are back to almost 3.5 billion years old. When scientists are looking for life on the Earth back around that period of time, it's a very difficult thing to do. One thing is because we have weather and we have climate that will destroy that evidence, or can destroy that evidence. So there are not that many places where we can find evidence of life that is that old. Okay, so a quick overview of the mission. The mission launched in it launched in August 30th of 2020. There's about a 7-month cruise. We're then, at the end of the cruise, we're going to enter the atmosphere and land on the surface. The landing system is essentially a copy of what was used on MSL. And then the surface mission is going to begin. The surface mission is qualified for 1.5 Mars years. And a Mars year is roughly 2 Earth years. So we're looking at about a 3-year nominal mission. And the Mars 2020 mission is the first in hopefully 3 missions. The Mars 2020 mission is going to collect samples. It's going to prepare those samples and store them on the ground. And then another mission is going to come by, pick them up, and launch them into orbit. Once they're launched into orbit, a return vehicle will come by, snag the return capsule, and take it back to Earth for processing. Now, the Mars 2020 mission, the reason why I talked a little bit about Curiosity is the Mars 2020 mission is going to look a lot like Curiosity. The real major difference is that we have a new set of tools and science instruments, such as the sampling system. So this just shows the science payload. As I mentioned, we have a science team that's made up of hundreds of scientists from around the world. Our instruments also have deliveries coming from places such as Spain, France, and Norway. The payload was selected through a competitive process, and that process was designed to create an instrument suite that supported the mission objectives. So let's get into the details of the sampling and caching architecture. So the sampling and caching system really is two robots. There's a robot on the outside and a robot on the inside. On the outside, we have a robotic arm, which is like the MSL robotic arm. It's about 2 meters long, and there's a turret on the end of it. The kinematic architecture of this arm is about the same as MSL. At the end of the arm, there's a drill. The drill is there to core. It's also with different bits on the end of it. It can abrade surfaces. The purpose of abrading is to remove weathering from the surface so that the science instruments can see the fine detail and really characterize what the surface rock and minerals or what the constituent rocks and minerals are. It's also there to collect core samples. And for the first time this mission, we're going to perform tool exchange, bit exchange. The second robotic system is the robotic system on the inside. And that system is there to prepare the samples. It's there to assess the sample, to prepare the sample, to seal the sample for future pickup, and to drop it onto the surface. The robotic system on the outside interacts with the robotic system on the inside through the bit carousel, which we can see here. On the outside, we use the bits, and the currency is a bit with a tube within the bit. Once we get to the inside robot, the currency that we use is the tube. It acts on the tube with the sample in it. And then eventually that tube, once it's prepared, gets dropped onto the surface of Mars. And I wanted to show this really quick video just to show you an animation of the sampling system, and then we'll go through a little bit more detail of the process. So our 2 meter long robotic arm is deployed. It positions the drill above the surface and makes contact with the surface. And at that point, the coring drill drills into the ground and collects a core sample. Once that happens, the arm retracts from the surface, and it goes and it docks with the carousel. We'll talk about some of the details of the docking activity from a robotic standpoint shortly. The bit with the now filled tube is dropped off into the bit carousel, and it rotates it around and it presents it to the robotic system on the inside. On the inside, there's a robotic arm called the sample handling arm. It pulls the tube out of the carousel, and then it performs a number of operations on the sample. It measures the volume, it takes pictures of the sample to determine and document what our sample looks like. Okay, so stepping through the SCS hardware activity. So on the outside, we have the robotic arm. It's there to place contact instruments relative to the surface to help characterize what the surface is made of. We use an abrading tool to abrade away the weathered surface. Then once that's done, we exchange bits. We drop off the abrading bit into our carousel, and we pick up either a coring bit or a regolith collection bit to collect samples. We collect the sample. Then we go back to the carousel and exchange the bit. And the robotic arm within the sample handling arm within the ACA pulls the now filled tube out of the bit. We then go over to a camera and take images of the sample to document what we actually got into the tube. And we have what we call a volume probe, where we can determine what the length of the sample is. Once that's done, then we want to hermetically seal the sample tube. We go over to a dispenser. We use the action of the arm to press on the dispenser to dispense a seal. And we go over to a sealing station, and that activates the seal. Once that's done, then we store the sample tube, the now hermetically sealed sample tube, on board. And we repeat that process. We can collect up to 43, or roughly 43 samples. What we do is we'll want to collect like 5 or 10 at a time, and then we'll find a good spot on the surface of Mars, and we'll drop those samples onto the surface of Mars for the future mission to pick them up. Okay, so what are some of the challenges for for the robotic system on Mars? Well, I group those into 3 main areas. One is that Mars conditions are different from Earth conditions. Another is that we have a series of hardware limitations that I'll get into momentarily. And then finally, there are operational limitations. Starting out with the Mars conditions, for starters, Mars gravity is approximately 38% of Earth gravity. So what does that mean from a robotic system? So imagine that we were going to command a robotic arm to a set of joint angles to go to a pose on Earth. If we were then to command the robotic arm to that same set of joint angles on Mars, due to the difference in gravity, the position of our tool would be higher. So we have to compensate for that. And I'll talk in a minute about how we do that compensation. Another thing is that Mars atmospheric temperature and pressure is much different than Earth. On Mars, through the course of a day, and also from winter to through summer, atmospheric temperature can vary by more than 100 degrees Celsius. So there's a pretty harsh change in temperature from one extreme to the other. And in most cases, we're operating at temperatures well below 0 degrees Celsius. So our hardware and our sensors have to be capable of surviving those conditions. Another factor, a challenge for the development of the robotic system, is unknown characteristics of the rocks that we'll sample from. When we're driving around and we pick a rock that we want to sample from, we're looking at essentially the surface of the rock. We don't know what's going to be below the surface exactly. So we have to develop a sampling system that is capable of dealing with a range of rocks. And we do that through testing on what we call analogs. There's a range of rocks that we select on Earth, and we want the system to be able to sample on Mars over that range. In terms of hardware limitations, the mass of the arm and turret makes up nearly 10% of the mass of the entire rover. So the entire rover is on the order of about 1,000 kilograms. So given that the mass of the arm and the turret's about 10% of that, interacting with the surface or moving this arm around in space can impact the rest of the rover. And it can affect our ability to actually accurately position the arm or to preload a surface. So we have to compensate for that. Another hardware limitation is CPU processor limitations. The CPU that we use is a PowerPC 750. It's about 200 megahertz, a 200 megahertz processor. There's limited memory. And the reason behind that is that the CPU has to be radiation hardened. It has to survive radiation in space. Another limitation we have is power. The amount of power that the rover is operating on is about 110 watts, which is about the power for a bright light bulb. And then finally, there are kinematic limitations. We'll see it in a minute with our big robotic arm and our sample handling arm. I'll talk about that momentarily. From an operational standpoint, there are limited communication opportunities with the rover. The way that it tends to work is we receive all the data from the previous day's activity. We plan out the entire day's worth of activity. We upload that to the rover through our deep space network. The rover then executes that day's set of instructions, and then it reports back to Earth how it did. The rover and Mars are too far away to have a ground in the loop joystick approach to operating the robotic system. You have to create all your instructions and be confident that those instructions are going to be reliable and perform what you need to do. Also in that, given the limitations of the CPU and also our onboard storage, there's a balance between how much data can you save on board, how much can be downlinked in these communication passes. Another operational limitation is target specification from imagery. This mission has a great set of cameras. The resolution of these cameras is much higher than what we had on the Mars Science Laboratory. And as such, the 3D terrain models that we can generate are potentially of much higher quality. However, that does come at a cost. There's a limited amount of data that you can send from the rover back down to Earth on each compass. So you have to be very judicious with how you spend that memory and that data volume, and what the quality of those images are. Furthermore, we have tight accuracy requirements for sample drop-off that I'll talk about in a moment. And then there's cleanliness of the sample. As we're taking these samples on Mars, the absolute worst thing we could do is acquire these samples, spend all the effort to bring them back to Earth, and then to find that, or not be certain that anything that we find is the result of something that we took with us. We don't want that to be the case. We want to be confident that when we open these tubes and we look at the samples, what we see is something that came from Mars and not something that we took with us. And then finally, we need to avoid collisions between the arm and the rover mounted hardware. Okay, so force sensing enables our sampling and caching functions. It's critical for pretty much everything that we do. Previous missions like MSL did have force sensing, The Curiosity robotic arm had a force sensor. It was a reduced degree of freedom force sensor. We didn't actually use it for force control. We used it for fault protection. For instance, if we were to bump into something with the turret inadvertently, it would trigger a fault and stop us. Now with the Mars 2020 rover, force sensing's really, a lot of what we do is predicated on our ability to do force sensing and control. We have a single weight up bit force sensor within the coring drill, and we have 6 degree of freedom force sensors on the Shaw and the robotic arm. Those sensors are used to perform activities such as force nulling. We use the robotic arm to preload the drill onto the surface. Imagine a person who's using a jackhammer to jackhammer into the ground. They're serving the role of the arm, and they're pushing the jackhammer onto the ground. The force sensor facilitates that. It also is used to do things like force nulling. As we're drilling into the ground, we want to avoid side loads on our drill bit, and the force sensor is used when we apply that load from the robotic arm. We want to make sure that we don't have side loads, and the force sensor is used to do that. It's also used for load limiting, and on the sample handling arm within the rover, we have a 6 degree of freedom arm that performs and is used for a lot of our station interaction. One of the things, going back to the challenges, I mentioned that we have huge temperature swings on the surface of Mars, and we're operating well below 0 degrees Celsius in a lot of cases. Well, we're starting to operate in the regime where force sensors traditionally have had trouble operating. So there was a lot of work that had to go into making sure that we had force sensors that were reliable and could operate at those low temperatures. And you do sacrifice a little bit of accuracy when we're talking about, as technologists, we think about force sensors that we use in our labs, and those force sensors have accuracies of the Newton level or sub-Newton. The force sensors that we have here have accuracies on the multiple Newton level. And a lot of analysis has to go into making sure that our force sensor accuracy budget will support the needs of the operations. And then finally, these force sensors also have to be fault tolerant. We have to make sure that if we lose a channel on these force sensors, it doesn't take our system down. Okay, so I talked a lot about this slide. I know I'm getting a little bit tight on time, so I won't get into too much detail. So we have the robotic arm. It positions and preloads our turret-mounted tools and instruments on the surface. The robotic arm's accuracy is measured in centimeters. We'll talk a little bit about ways that we can improve upon that. One of the ways is through the use of a facility contact sensor. That helps us to localize where the ground is. We come down and we can make contact, and then we can switch over to one of our science instruments, either Sherlock or Pixel, and then perform a science observation relative to where we contacted. The robotic arm also is used to perform kind of what I would call the gross level positioning on the order of a few centimeters. And then if you look at instruments like Pixel is mounted on a hexapod, and that hexapod is used to perform that fine level position tuning. We also have capabilities such as Pixel has what they call OFS, or optical fiducial system. It uses structured light to measure what the surface looks like relative to the instrument to do that fine positioning. Sherlock has cameras that can determine range to the target based on focus, and we can use that information to improve upon our positioning accuracy. Going back to our drill, so our drill is a multi-purpose drill. We use it for abrading the surface to remove weathering. We also use it for coring and regolith collection. And we can see some of our flight bits in the corner. They're coated in tinitride. As I said, any piece of hardware that we call sample intimate hardware that's going to come into close proximity to the sample needs to be very clean. And the coating on these bits is such that we could bake them out to very high temperatures, and it made it easier to clean those, to destroy any organics that were on the bits, and to destroy any microbes and burn them off prior to launch. Okay, so when we're doing a positioning exercise, when we're coming down to acquire a sample, the coring drill has stabilizers on the end of it. The stabilizers articulate. So one stabilizer will contact first, and then the other stabilizer makes contact, and the drill will then conform to the surface. And once that happens, there's a contact sensor within the drill that will stop robotic arm motion. And once we do that, we can then proceed with our sample acquisition. The drill will use its feed to extend the bit out to make contact with the surface. We use the weight on bit sensor within the drill to maintain force, and we sample using rotary percussion. So we're rotating the bit as we're percussioning on the surface to acquire a core sample. Once we've gotten to a certain depth, we then break the core off, retract from the surface, and then go to the carousel to drop the sample off. So docking and bit exchange is how the external robotic system interfaces to the internal robotic system. It's used to exchange bits, and it's also used to drop off the sample, the now filled tube that has a sample in it, to feed it to the internal sample processing system to process the sample. The docking process reduces the robotic arm positioning and orientation errors. As I mentioned, the robotic arm, due to the mass of the turret and the stiffness of the arm, and also the rover, the positioning accuracy, the uncompensated positioning accuracy of the robotic arm is measured in several centimeters. We can calibrate the arm to reduce that uncertainty down to a few centimeters. However, when we're trying to do bit exchange, we have to achieve accuracies at the sub-millimeter. The alignment has to be sub-millimeter in order to drop that bit off into the carousel successfully. And our docking process helps reduce that error. The robotic arm, and I'll talk about docking in a second. So in terms of the hardware for docking, we have the drill side, and we have the bit carousel side. On the drill side, we have posts, 4 posts on the outside of the drill. They're alignment posts for aligning the drill with the carousel to achieve our positioning, our tight positioning accuracy. On the docking side, we have docking cones. So those docking cones they have the proper diameter in order for us to achieve initial capture. There's also a passive rotary rotational degree of freedom on right here. There's a passive rotational degree of freedom that's in place. Why do we have that? As I mentioned, our robotic arm is a 5 degree of freedom robotic arm. Obviously there's 1 degree of freedom that you can't control, and it's the rotation about the axis of drop off. So we have that passive degree of freedom there, so that the dock will conform to the rotation of the robotic arm. We have contact switches at the bottom of our cones. They detect when the docking exercise is complete. And finally, there's a resolver. The resolver measures the rotation of this passive degree of freedom. And the reason we need that is as we drop the bit off into the carousel, the orientation of that matters. So as the robotic arm comes in and docks, this passive degree of freedom will rotate to conform to the arm. The resolver will measure how much that degree of freedom rotated. And then we can use the rotational degree of freedom of the drill to compensate. So docking, the way that we dock is a process called force-corrected docking, which is what we call our discrete force control. And here are the steps for that. So we have our 6-axis force sensor on the robotic arm. The robotic arm positions the drill such that the docking posts are a few centimeters in front of the docking cones. We then move to contact. Once we move to contact, we look at the force sensor and we measure our forces and moments. And then using that information, we can correct the alignment. So we come in, we push, we measure the forces and moments, we do a correction, and then we push again. And we repeat that. That's why I refer to it as discrete force control. And eventually the docking posts will be located at the bottom of the docking cones. And once we get to the bottom of the cones, we then apply an additional preload so that we can successfully drop the bit off. Oh, sorry. Okay, so in terms of robotic arm accuracy, as I mentioned, the robotic arm has an accuracy, an uncompensated accuracy that's measured in many centimeters. And we improve upon that positioning accuracy through calibration. And this is a fairly standard methodology for doing that. We move the robotic arm through a number of poses. We have a laser tracker system that shoots points on the turret of the robotic arm, the end effector of the robotic arm. We record the joint angles, and we collect on the order of about 80 poses worth of data. We then use that data to calibrate our kinematic and stiffness model. And that's how we compensate for the difference between Earth and Mars. Our stiffness model has gravitational components to it. And you can set the parameter for Earth operation or Mars operation to do the compensation, whether you're on Earth or Mars. Okay, so then there's just a quick video of the robotic arm being tested in our high bay to give you a sense of the size and scale of it. As you can see, our end effector is huge. It's pretty massive. It's on the order of about 100 kilograms. So that's a challenge for an arm to be able to position such a massive turret accurately. So then we have the adaptive cache assembly. That's the robotic arm and the robotic system within the rover. Operations of the for the robot within the rover are performed using the sample handling arm. It's a 3 degree of freedom robotic arm. There's a Z stage for linear motion, and then 2 rotary joints. And that robotic arm is used to interact with all of our stations. We have sample tube storage, we have a bit carousel, we have volume assessment, so on and so forth. And one thing that I'll point out is that we have our sample cleanliness concerns and requirements. All these stations have covers on them. So this SHA, this sample handling arm, has to manipulate the covers. We also have what we refer to as gloves. So the gloves are between the sample handling arm and the tube itself. And they function much the way that a glove works when a scientist or a doctor wants to make sure that their hands are that they're clean. Essentially, the glove is serving that same purpose. Our sample handling arm is clean, but it's not to the level of cleanliness that we want to maintain the sample in its integrity. Now, I mentioned that this is a 3 degree of freedom robotic arm, and I imagine that most of the kinematicians and roboticists are screaming in their heads, well, if it's a 3 degree of freedom robotic arm, how do you hope to be able to interact with these stations? It shouldn't work unless everything was perfectly aligned. And the way that we do that is we have an RCCM, which is a remote center of compliance mechanism. So it complies and it makes up for positional inaccuracies of both the arm and also misalignments in our stations as well. At the end of our end effector, we have our 6 degree of freedom force sensor that is used to do our discrete force control as well. So then just wrapping up, here's a cool picture of our testing the ACA. This is an engineering model of the ACA. We perform tests both at ambient conditions and at Mars conditions. A big part of why we've been so successful in our missions is that we test, test, test. That's a big part of the mantra. And then finally, when I talked about communications with the rover. I think I've already covered this. Mars is anywhere from, in terms of one-way communication, it's anywhere from 5 to 20 minutes away, which really does preclude us from doing any joysticking. That's why when we build our instructions for a day's operation, we have to be very confident that those instructions are going to do what we expect them to do. And as a result of that, fault protection is very critical. We need to make sure that our system can't hurt itself, or we'll get into any situation that can't be reversed. Okay, and this is a video and for the sake of time, I think I'll skip through this. Wrapping up, these are 2 of my favorite pictures. This shows our hardware right before we launched. This is right before the spacecraft was buttoned up and put onto the rocket. We can see our robotic arm, our coring drill, and then at the bottom, here's our sample handling assembly in our robotic system on the inside. And then there's a zoomed in picture of that. Now, what I should say is that these pictures are my second favorite picture. My real favorite picture is this. Here's a picture of the members of the Mars 2020 team. This was taken about a year ago. It shows that it takes many, many people from all over the world to pull off a mission of this magnitude. And I'm very happy to give you a little bit of insight into what this mission is about. And I hope you have taken away a little bit of the excitement that we feel for this project. And it's landing in February of 2021, in a few months from now. So we're preparing for surface operations.
All right. Can you hear me?
Yes.
Right. Thank you very much, Matt, for your talk. You gave a very nice overview of the Mars 2020 mission and of the sampling subsystem. The complexity of it is really, really amazing. Would you mind turning your camera back on?
Yeah.
And as usual in Robotics Today talks, now we're going to have questions from both the panel and the audience. If you are in the audience, I invite you to submit your questions through the Slido interface on the Robotics Today website. And I'd like to introduce the panel. So today we have Alberto and Luca, which are co-organizers of the Robotics Today seminar series. We have as guest panelist Professor Bechet Asekmechis from University of Washington. And we have an additional panelist, Professor Monroe Kennedy, who is a new organizer. So he's going to help me, Bert, and Luca, and Jeanette going forward in putting together this series. So I would like to quickly introduce both the guest panelist and the new organizer. Bechet is a professor in aeronautics and astronautics at the University of Washington, and his research focuses on guidance, navigation, and control, and optimal control more broadly. In particular, Bechet, actually met him for the first time when I was a technologist at JPL. He pioneered, I would say, the use of convex optimization techniques for autonomous spacecraft guidance. He's a very humble person, so he won't acknowledge it, but behind, for example, the success of some of the SpaceX mission, there is certainly a little bit of Bechet in there. Before joining the University of Washington, Bechet was a technologist at the NASA Jet Propulsion Lab, where, among other things, he developed and delivered the guidance and control algorithms used in the flyaway phase of the successful Curiosity Rover mission. In turn, Monroe is an assistant professor in ME at Stanford, and he's the director of the Assisted Robotics and the Manipulation Lab. And his research interests broadly are around assistive robotic systems and more general systems that help improving everyday life by properly interacting with humans. That said, I would ask Bechet to start with his questions. After then we'll take some questions from the audience and we'll proceed from there. Bechet.
Can you hear me, Michael?
Loud and clear.
Yeah. Matthew, thanks for the great presentation. It's nice to see that 2021 will most likely land safely and it will do great. I mean, I'll start with a more general question. Among all the things you worked on, you know, what excited you the most in terms of both the project specifically, but also in terms of the new technology possibilities or hints that are in the project and that will carry themselves over to the next projects and so on, you know. If I'm making sense, if you had worked on some pieces that you thought, okay, we did some new things here, but you know, I can see that further steps can improve what we have done, and maybe in the next mission we can add these capabilities and demonstrate them on the next significant mission.
Oh yeah, absolutely. Can you hear me?
Yep.
Okay, good. I see a message that says my speaker may not be working, but great. One of the exciting things about the missions I've worked on is with each mission, the robotic complexity is increasing. And what we're asking these missions to do, from a positioning accuracy requirement and from a load application requirement, is increasing with each project. And even from the last mission to this mission, we went from the previous mission was actually the first time that we had flown a force sensor on a Mars rover at all. And we that was almost what I'd call a technology demonstration. And we didn't use it to actually, since we were demonstrating that technology, we didn't use it to actually in the control loop. We used it to as a kind of a belt and suspenders to help protect the arm. Now with this project, as the requirements got more stringent, we realized early on that the arm's positioning capability alone just isn't sufficient to do things like bit exchange. We have to have that force sensing capability to do that fine alignment. And now our approach to doing that is fairly simple. It's what I refer to as a discrete control. It's kind of you reach up, you feel and what those forces are, and then you adjust and feel again and adjust and feel again and adjust. But it works, right? But even with that, it's a huge step forward. The fact that we're doing also that we're doing bit exchange, tool exchange. That's something that's very new to this mission as well. So from a robotics standpoint, we are taking big steps ahead in where we were in terms of what we're asking the robotic arms to do. And from a vision standpoint, for instance, we don't do a lot of, or we don't really do much vision in the loop control, but that's one of the areas where I can see that we could get away from the reliance on all the work that we do to do all these calibrated models. We could do some vision in the loop to simplify that potentially. And that's one of the places where I see that we could potentially make a big leap. Now with Mars missions, as you're probably aware, given how hard it is just to get there, the missions typically want to do just what's good enough to make it work, right? You don't necessarily want to, and you have to also demonstrate that your technology and your approach is bulletproof, that it's going to work, it's not going to have problems, right? Because if you have problems on Mars that are a result of the technological flaws, as a result of that, it could be a potential life ender for your mission, right? So, the missions are very careful not to dive into technologies that aren't absolutely necessary. However, we're getting to the point where, in order to meet our scientific goals and our scientific needs, we need those technologies. And I think the next level of force sensing, to do that next level of continuous force sensing control, I think potential vision-based control to do vision-based positioning, and both in terms of to improve upon our accuracy with positioning instruments, and also to eliminate our reliance upon these very complex and very complicated kinematic and stiffness models. They're reliable, and that's why we use them, and they've been good enough. But I think as we keep moving forward, we're gonna get to a point where there's a limitation on what we can get out of that approach. So that's one of the things that I would say. I think also other technologies I think would be very exciting would be, so we do bit exchange, right? We exchange tools, but that's a mechanical process. So the capabilities such as to swap out powered components is another leap in that technology, which would be pretty exciting. Where if you had a component that you had a problem with, and a component that's potentially a little less reliable, you could go swap it out for a new one. But that might need, you may need to have powered the ability to swap a powered component as well. So I think those are some of the technologies I think that we'll continue to push forward on robotically.
Thank you, Matt. I mean, I have some more, but I will let others ask. Then if I have time, I'll ask more. Is that okay, Michael?
Sounds good. Thank you.
So I think next we have a question from Ransalu, who is speaking a question from the audience, right?
Yeah. Okay. Thanks for the great talk, Matt. Yeah, so I see you have tested this system a lot. Like, so when we work with hardware, especially in unknown and unexplored environments, so there can be hardware failures, right? Mm-hmm. So the question from the audience is, what backup systems do you have in case something goes wrong?
Okay, yeah, that's a great question. We have a number of backup systems. One that I alluded to was on our force sensors. Since our force sensors are absolutely critical to our operation, we made sure that they're tolerant to the loss of any single force channel. So we could lose a force sensing channel, and we have backups that we can use. We can use other gauges to still produce the forces and moments that we need to perform the operations. So there's redundancy in our force systems. That's one. That's a big part. Also, on our sampling system, the picture showed it, but I didn't really talk too much about it. We have a number of drill bits, right? We're carrying, I think, 3 or 4 drill bits, so that if we're drilling into the surface and something happens, the rover shifts and that drill bit gets stuck in the ground, we're not just stuck there as a rover. We could jettison that drill bit if we had to. Now, we're not going to immediately jettison it. We'll try to use the force sensor to get our way out. But if push came to shove, we could drop that drill bit on the ground and we could go grab another one. So we have redundancy in our sampling drill bits. We have redundancy in our force sensing capability. We have imaging redundancy. I didn't get into that because I could spend the next week talking about the 2020 mission and really only stay on the surface. We have something like 20 some odd cameras on this rover. We have cameras that are body mounted and mast mounted. So if you lose one set of cameras, you have other cameras that you can use to generate your terrain models. We also have redundancy in the science. There is some overlap in some of the capabilities of our science instruments. So if you were to lose one science instrument, it doesn't mean that you can't collect that information. That's part of it, is the redundancy, but also the correlation of observations too. You want one science instrument to verify what the other one got from results. So we have lots of areas of redundancy. On our contact switches, a lot of them have mechanical and electrical redundancy too. Yeah.
Hi, Matt. So I have a question from the audience. They actually are interested in hearing about what your planning algorithms are like, specifically, for example, for the arm. I know you mentioned that self-collision was a problem, something to watch out for in terms of getting the arm moved around the vehicle. Is that something that, are you guys doing online planning? Is it a library of trajectories that you're doing, on the ground and then flying in the air? Or I don't know if you can kind of elaborate on that a little bit.
The operation is planned out on the ground. So we plan out all the motions on the ground, but that doesn't mean that what's going to happen on Mars is going to be exactly the same. And why is that the case? There are certain activities that we perform where we're positioning the arm relative to gravity. And in order to maintain a certain gravity position, it's dependent on what our RIMU, our inertial measurement unit, tells us our orientation of the vehicle is, right? So that's a measurement that's taken in situ, and that can change our trajectory as a result of that. So the basic plan of motions is the same, but that doesn't mean that the inputs to that motion won't affect what happens on Mars versus on Earth, if you follow me with that. Also, if we're performing absolute movements, move to some absolute XY position, that should be pretty repeatable on Earth or Mars when we plan on Earth versus what happens on Mars. But if you're performing a number of relative motions, those relative motions will depend on exactly where the previous motion ended up. So there could be a buildup in differences between what happened when your plan, what your plan said was going to happen, and what happened on Mars. But in terms of path planning to autonomous path planning on the rover that adjusts to avoid collisions, we don't do that. In fact, we don't really need to do that. The collision checking is there for what I talked about, for those slight differences. If your REMU changes your trajectory a little bit, that puts you too close to the rover, it's going to detect that you're getting too close, or you're too close, and it's not going to allow you to perform that activity, that motion.
Do you ever think that the long delay that you also talked about in the communication is ever kind of something that in that kind of planning can make that planning loop kind of more difficult, in terms of if you always have to go back to the ground in order to kind of have that feedback from that operator? Is that ever kind of an issue?
Well, oh yeah. I mean, certainly the ground in the loop does present challenges, right? You plan out an entire day's activity and you execute it, and if something didn't work quite right in that set of activities, now you have to diagnose what went wrong and figure out how to move forward, right? And then you upload a new set of instructions, and then that new set of instructions gets executed, and you have to wait another day, right? So it can take time to recover from an issue. That's a big part of that communication limitation.
Thank you, Matt. I have a question from the audience. How does the rover perform navigation on Mars?
It does. The rover. So there are two ways that we can do navigation. One is, so as I mentioned, we get all the data for the next day's activity, and the cameras can see, our mass mounted cameras can see out to maybe 100 yards. So you can manually plan out how that rover is going to drive for the first 100 yards. Now, after that, we then go into autonomous planning, onboard planning, where the rover will do path planning for how much time you have remaining in the day. You can switch to an autonomous onboard mode. There are a number of path planning methods. I don't remember off the top of my head, because that's not my area, exactly what we use for path planning, but there is onboard path planning capability. We have stereo cameras. It can take images on the surface. It can then detect terrain obstacles. You know where you want to go. You have an endpoint goal, and then it can path plan on board to get there. Now, the autonomous onboard path planning tends to be more computationally expensive. It takes longer, so that ground in the loop first 100 yards or so can happen fairly quickly, because it's essentially a blind drive. That last few meters can almost take as much time where you're doing the local in situ planning. I think that answered your question in kind of a general way, but.
Thank you for the great talk. I wanted to ask, so in case So it's a question related to the audience. In case the rover faces problems on Mars, so you have a replica to simulate what could happen with the rover there. But since the conditions on Mars and Earth are different, as you mentioned, are the rovers built exactly the same way, or are they different? And just to follow up on that, if they're the same, what do you have models to convert and how to convert the data you would have, and how realistic are they?
So we have two ways that we can attack that problem. One is we have an engineering model version of the rover that we can test on Earth. Now that testing tends to happen in ambient conditions. We test that in our what we call our Mars yard. Now it's built exactly or as close to an exact copy of what we send to Mars, almost an exact copy of Perseverance. We want it to be an exact copy. From a robotic standpoint, we have software and parameters that accounts for the difference between Mars conditions and Earth conditions for things like gravity. So that's one thing. With respect to Mars conditions like pressure and temperature, we have chambers. So we have a 10-foot chamber that can go down to Mars pressure, and we can cool it down to Mars temperature, and we have an exact copy of our sampling system. So we have rock stations where we can do sampling, and we can process that sample just like we would on Mars. Now, the great thing about that is if we run into a problem on Mars, we can try to replicate those conditions in our environmental chamber as close as possible, and use that to figure out ways to recover. And that's also a way that we can increase our recovery, right? So we can try out many things in our environmental chamber on Earth, and then pick out the best approach, and then upload it to our rover on Mars. So we're not doing trial and error on our Perseverance rover. We're doing that within our chamber on Earth, and we can test out many cases here.
Thank you, Matt, for a wonderful talk. I have a quick question about when you were talking about communication for the rover. Does the rover communicate directly with Earth, or are there satellites that are actually there that can perform as a relay or a buffer? And if so, does that help with like streaming? I'm thinking about that bandwidth there.
Yeah. So we actually have both direct to Earth capability and there are a number of orbiters that are orbiting Mars that serve as a communication relay. And so what we do is we create our instructions. They go to these big, huge antenna arrays in the Deep Space Network. They get relayed up to the orbiters and then down to the rovers. And then at the end of the day, that path is reversed. So from rover to orbiter back to Earth. We do have direct to Earth capability, but the direct to Earth capability is a much lower bandwidth. We can't communicate as much information, and that's really there. So most of our science data is going to come down through the orbiters. The direct to Earth is really if you have a problem where you need to be able to talk to the rover and you don't want to wait on a compass, on an orbiter pass, you could talk directly to the rover, but you're gonna have very reduced bandwidth. There's gonna be a limited amount of data that you can transmit back and forth, and certainly not enough bandwidth to really try to do a science operation. It's just more of the what I'd call a Hail Mary or you're in trouble and you want to and you need to recover quickly. Yeah.
So Matt, thanks for the great talk and for the great overview. I had a question, and I'm sure that's on many of the attendees' minds. So the question is about ingenuity, right? So I guess that on board you also have an helicopter this time, which is something like fairly unique and fairly exciting. My question is there an interaction between the robotic arm and Ingenuity? What is the system to deploy the helicopter in the first place? And how do you guys make sure that the rover and the helicopter are not colliding with each other, let's say?
Yeah, I knew a question about ingenuity would show up, and I thought about putting a picture in there, but I pick and chose what I was going to include here. And the Mars helicopter is a super exciting thing. We're super pumped about that. In fact, just to provide a little background, if you look back to Sojourner and Pathfinder, the Sojourner rover was actually a technology demo. And it was such a successful technology demo that it led to MER, and then from MER to MSL, and MSL to Mars 2020. So it spun off all these rovers of increasing complexity and increasing capability. In the same way, Ingenuity is a tech demo. And depending on how it performs, I could see that being a potential revolutionary thing, technology. So it's pretty exciting, and we're pretty pumped about it, and we think it's awesome. Now, so Ingenuity is stored up under the belly of the rover, and there's kind of a deployment, or not kind of, there is a deployment device, almost like an arm, that deploys Ingenuity to the surface and drops it off. And then once that happens, the rover will then back away. Now, when you hit a perfect point about the safety, right? We want to make sure that the helicopter doesn't interfere with the rover, or we don't get in trouble where something goes wrong. And so the idea is that the helicopter, the rover will back away, the helicopter will fly off, and it'll stay maybe 100 meters away or so at all times. So it'll keep a healthy distance away from the rover. Now, there's not a huge payload on the helicopter. There's essentially a camera system. But the cool thing about that camera system is that camera system can go take images outside of the rover's horizon, outside of what it can see. So it can help map the terrain and find interesting locations. It can help us decide where to drive, right? So right now on MSL, where we decide to drive is from orbital imagery, outside, beyond our horizon. So we have our 100-meter or so horizon that we can see from the surface of Mars. Then we augment that with orbital imagery on MSL. Well, now on Mars 2020, we have this helicopter that could be 100 meters or so out further, and it could help scout out where we might want to go. So that's a really cool thing. It's almost a pathfinder for us. So that I think is one of the really cool aspects of the helicopter, that it can provide that service. Now, from a robotic arm interaction, the robotic arm will really be used to, once we deploy the helicopter, the robotic arm has a camera on the end of it. We'll take pictures underneath the rover to show that the helicopter was deployed successfully and it's healthy and everything looks good. So that's a big part of it. Now, the robotic arm, we have a capability that we call making selfies, right? Everybody knows what a selfie is. So you take your camera and you hold it up and you take a picture. Where our selfies, and you got that in your background, it's not a single picture. It's actually a composite of I think 50 some odd pictures. And one of the cool things that I think that we could do, and we should do for 2020, is have the helicopter somewhere off in the distance and take a selfie of the rover and the helicopter if we can. So I think that'd be a really cool interaction.
It's truly amazing. I noticed that the design and the visual navigation system of the helicopter is pretty aggressive. It's pretty advanced. So I'm really, really excited to see that being deployed and see what's going on. So thanks for the reply.
Yeah.
All right, Matt. That was fantastic. We could spend the next few hours asking you questions, but unfortunately we're out of time. So I just thanking you for taking the time to be here with us and for giving us a perspective on the state of the art and a bit of a retrospective on robotic technology for planetary exploration. And I guess thanks for sharing amazing pictures with us and great videos, and also for the beautiful words you had at the beginning. Let's all persevere.
Thank you.
And before finishing, I just wanted to mention that in 2 weeks, we will have, on October 16th, we will have Kristen Peterson. She will give the next talk at Robotics Today. And she's from Cornell University and is the director of the Collective Embodied Intelligence Lab. So quite a shift from today's talk. What if we could send 1,000 mini rovers to Mars? How would we do that? Anyway, thank you everyone for connecting, and see you in 2 weeks.